Hey guys, so in this video, we're putting together what we've learned. We've talked about several things. Linear regression, which we said is modeled by this. We've also talked about the cost function, and we represented the cost function as this. And we've also talked about our gradient descent algorithm. And for our gradient descent algorithm, we said we would basically repeat until convergence following. And just to remind you, repeating until convergence means when our cost function gets to 0, when we found the parameters of w and b that make our cost function go to 0. Okay, this was all review, but it turns out this partial derivative here is actually equal to the following. 1 over m summation I equals 1 to m of this. And this portion right here, this partial derivative, is actually equal to this. And you might notice that these two right here are quite similar. And you might also be wondering, what the heck, where did we get this from? Well, I'm going to derive it for you right here. This derivation does include some calculus, so if you don't understand it, that's fine, you can skip along. It won't affect your understanding of what machine learning is, but if you do want to stick around for the derivation, here it is. So we will derive these right here. And these are important because instead of a derivative, we use summation, right? So this was derivative, this is summation. And when we integrate this with our code, it's much easier to do iterative algorithms, which is why we convert that partial derivative into an iterative algorithm, right? So into summation. Okay, so let's do the derivation right now. So we took the partial derivative with respect to w of our cost function here, right? In gradient descent right there. So if I were to expand that, that's a derivative with respect to w of our cost function, which is this portion right here, okay? So this is the partial derivative with respect to w of our cost function, which is 1 over 2m. Okay, and it turns out, by the rules of calculus, if we were to take this derivative, we would get this. Okay, so we can expand this portion right over here into this. The partial derivative with respect to w of 1 over 2m, and this summation, and we can rewrite our function as this, which we've already established. This should be very familiar to you. Wx plus b, and then of course, it's just going to be subtracted by the true value. Okay? So we have that. And by the rules of calculus, if we were to take this partial derivative, we would actually get this. 1 over 2m summation I equals 1 to m of the inside multiplied by 2x. Okay? And if you see, the 2's actually cancel out here. This cancels out. So what we're left with is this. And now you might realize, hey, this is why we added the 2 in our cost function initially. Because when we apply the rules of calculus, we actually end up with another 2 over here. And that helps with our simplification process. So that's why we included the 1 over 2m in our initial cost function. Okay, so this makes sense now, right? We can box this. This is our derivation for the partial derivative of the cost function with respect to w. Now, let's derive the partial derivative of our cost function with respect to b. Okay, this is going to look very similar to what we just did. So we're going to take the partial derivative with respect to b of our cost function. And I already expanded it here for you guys. Okay, so when we apply the rules of calculus for this one, it'll look very similar, just a bit different. So it's going to be equal to 1 over 2m multiplied by the summation, which stays the same. And then instead of multiplied by 2x, it's just going to be multiplied by 2. And this cancels out again. The 2's cancel out. So what we're left with is this right here. 1 over m times the summation. Really cool. Okay? So we can box this as well. And now, if we look at our updated gradient descent algorithm, it'll look something like this. We're going to repeat until convergence and what we've already worked with, but we're going to replace the partial derivative with respect to w of our cost function with what we just found. Right? We concluded that this is basically equal to the partial derivative here. Okay? So we're basically going to plug this into this right here. So our updated algorithm will look like w is equal to the previous value of w minus alpha times what we just derived. So it's going to be times what we just derived, 1 over m, and the summation. Similarly, we're also going to update b in the same way. So it's going to be b is equal to the previous value of b minus alpha times what we just proved the partial derivative of our cost function with respect to b is. We proved that this is equal to the partial derivative with respect to b of our cost function. And we have that right here. So we're just going to plug what we just derived, the long summation that we just derived, into our gradient descent algorithm. So it's going to be b is equal to the previous value of b minus alpha times 1 over m times the summation. Look at that, same summation as above with a slight difference. So it's really coming together here. But remember, this value of x is not here, okay? All right, and we're going to repeat until convergence that. Please note that we will be updating these values of w and b simultaneously, okay? Make sure you are updating these values of w and b simultaneously. If you don't know what that means, please check the previous video. And one thing I'd like you to know is when we're working with our squared error cost function, we actually won't have multiple minimums. So here, if we had a cost function that looks something like this, right? And we started over here, we might get to a minimum over here. But in a different scenario, we started with values of w and b that are over here. Because you can see the axes, right? We have values of w and values of b. So if we started with a value of w and a value of b that lines up right here, if we use gradient descent to find our minimum, it might get us to the minimum over here. So the minimum you reach to with different types of cost functions, like this one, for example, will get you to different minimums depending on the initial values of w and b, the initial values of your parameters. However, if you're using the squared error cost function, there will only be one minimum. You can see there is only one minimum here. There's only one minimum here. It's right here. It's not going to bring you to another minimum because there's only one minimum. So please note that when you're using the squared error cost function, you will only have one minimum. You will not have to worry about that. Okay. Hopefully you guys enjoyed that video. It was a bit intensive, but hopefully it, pieced together everything that we've been working with.